in AP Physics 2, we just learned that current can create magnetic fields. So if you think about the equation, B equals mu naught I over 2 pi r, it's just a way to mathematically show that current can create magnetic fields. But, if you think about all kinds of bar magnets, right? If we think about the north and south of a bar magnet, there's no current going through this, right? It's just a bar, right? And it still has a magnetic field. So how is that possible? How can a bar magnet be magnetic and produce magnetic field? And the answer lies between magnetic domains. And magnetic domains also help us explain how iron can be attracted, or nickel can, and then all these certain elements, how they can be attracted to magnetic fields and bar magnets. So a magnetic domain, really, it's like these sections. So I guess the textbook definition, or like what you would search, like what Google would tell you, is that like if you had, let's say this is just a bar of iron, right? Magnetic domains are these regions in the regions within the bar that have like the atoms are creating like this sort of, I guess, like small magnetic field, or really a magnetic moment. And if you take physics E, or if you are in college physics, it's really a magnetic moment, and then those magnetic moments can help create torques and all kinds of force and stuff. It's like these regions in the iron which are magnetized, but if they're not aligned, right, they're not gonna be the whole like bar, it'll kind of net out, all these alignments will cancel each other out, and there won't be a net magnetic field. If you think about a bar magnet, right, so if I draw a bar magnet has all of its like magnetic domains in one direction. It's all aligned. And that will in turn create like a magnetic field. So that's really what a magnetic domain is, but not every atom or every, I guess, element or every substance can really have magnetic domains, right? So if I take a piece of iron by this magnetic field, it's going to have those magnetic domains, but they're all misaligned. But what ends up happening is they're going to get aligned with the magnetic field, right? As it loops through here, these domains will end up facing this, will end up getting aligned, and then boom, right? Like it becomes its own kind of magnet temporarily. And then that's why iron things stick to magnets, or why nickel, or why cobalt, or whatever. But aluminum doesn't do that, or tin, or any other kind of element. Most elements don't do this, right? The reason is because, and this is from my textbook, so I might be explaining it wrong. If you're a chemist or something and you have a better explanation, please correct me. But I think the physics behind why not every material has domains is because domains are created by these clumps of atoms, and these atoms, like in an iron atom, the movement of electrons creates that tiny magnetic field. It's like if now this is like a simplification and kind of not true at all, because quantum mechanics is how you explain the motion of these kind of subatomic particles, and I don't know quantum mechanics, but the analogy is kind of like, if you think about your atom, there's going to be an electron spinning around, and hey, moving charge creates magnetic fields. So this is tying back to that idea of moving charge creating magnetic fields. It's the spinning of the electron. Now, in an iron, I think they all spin in kind of a uniform direction, so that there would be, and if you think about the right-hand rule, there's going to be a magnetic field upwards. I bet almost negligible, but when you have a bunch of atoms together, that's how you get those domains and get the alignment to create the whole magnetic field. But for atoms like aluminum or any other like non like ferromagnetic or non like magnetic atoms, the movement of the electrons is kind of random. So each atom kind of has no magnetic field, whereas an iron, nickel, cobalt, I think they all spin in kind of the same direction. I think that's what my yeah, it's like yeah, all the like a lot of the electrons like domains or like kind of magnetic moments as the textbook refers to, they all kind of align with one another. That's why certain atoms are magnetic and certain atoms are not. So or certain elements are not. So yeah, that was kind of just a brief little thing about magnetic domains. And if I magnetize something or like a bar magnet, right, which has all of its domains aligned, if I start banging at it or if I start heating it up or doing anything that kind of messes up the alignment, it's not going to be as strong of a magnet anymore. In fact, let me see. I think wait. Oh my god. I have like these like train thingies I have since I was a kid. I don't know why they're still in my room, but oh, I guess they still work kind of well. They have magnets to connect them, and I bet if I keep like banging or keep like tossing them around or keep messing with them, they're slowly gonna die because their domains are slowly gonna start like just misaligning. There's gonna be no more like net magnetic field. So hopefully that makes sense. Really, if you want to learn more, if you really want to get more in depth in this, I think you need quantum mechanics. But hopefully, this at least is simple enough for you to wrap your head around the concept and still be able to do the physics or the AP Physics 2 problem. So yeah, thank you for watching, and have a good day.